In this last video of Chapter 11, we want to look at how the periodic table has a number of properties that follow trends across the periodic table. And to begin that, we want to talk a little bit about how the periodic table came to be and how it was eventually developed. The periodic table comes from a Ukrainian scientist in 1869 by the name of Dmitry Mendeleev. He arranged the elements based on similar properties. And the genius in Dmitry Mendeleev's original idea of the periodic table was that he left open gaps in the periodic table and predicted the elements that would fill those gaps and what properties those elements would have. These were elements that were later discovered, and when they were later discovered, they had most, if not all, of the properties that Dmitry Mendeleev said that they were going to have. This allowed people to see that his idea of arranging elements by similar properties made a lot of sense and actually fit to describe the chemical world and all the elements very clearly. Our modern periodic law is that we take the properties of the elements and they reoccur periodically when we arrange the elements in order of increasing atomic number. Dmitry Mendeleev didn't have a full concept of atomic numbers and all of the various details we know about the structure of the atom at this point. However, he looked at the properties and said that they repeated, and we now know that if we put them in order of increasing atomic number, these properties do indeed repeat. Some of the regularities to the periodic table. The vertical columns, once again, are called groups or families. The horizontal rows are referred to as periods. We also have valence electrons. Valence electrons are the outermost S and P electrons. So we're taking the highest energy level and adding up any electrons in the S and P orbital. The reason I put S plus P, not P plus S here at the end is when you have the highest energy level, S will always come first. So you're going to take the S and P orbitals from that highest energy level. If you add the highest P plus S, could very easily get something that just started in an S orbital, and if you add the P from the lower energy level, you'll get the wrong number of valence electrons. So valence electrons always are between 1 and 8. 8, the noble gases, 1, the alkali metals, working their way across the table. Now we know that when the outermost orbitals, S and P, are full, the noble gases, elements tend to be non-reactive. Metals tend to lose electrons, and they tend to lose electrons because they have a small number of valence electrons, and therefore will lose those valence electrons to become isoelectric with the nearest noble gas. Nonmetals tend to gain electrons to form anions because to become isoelectric with the stable noble gases, the easiest for them to do is to gain a couple of electrons rather than lose a larger number. Now there are a couple of trends that we want to look at for properties that you can see based on the placement on the periodic table. You know which ones will be larger, smaller, higher ionization energy, lower ionization energy, various trends that we can see based on their placement on the periodic table. Atomic radius is the first one we want to look at. Atomic radius is the size of the atom. So if you have an atom and we were to think of it as a circle with the nucleus in the middle, the radius would be the distance from the nucleus to the outside of the electron cloud, the orbitals. The atomic radius follows a general trend. Now this trend actually goes against what you would think would happen just based on probably your preconceived notions and just the way you think this would probably occur based on the number of protons and electrons. What we find is that atomic radius actually decreases from left to right across a period. This doesn't seem to make a lot of sense to most people because as you go left to right across a period, especially if you drop down to the third or fourth period that includes the d orbitals of a lower energy level, as you go left to right, you can go from as many as, say if we get down to the sixth period, 55 protons, 55 electrons, and a mass number of 132, all the way up to radon, which has 222 as its mass number and 86 protons and electrons. Significantly larger number of protons and electrons as you travel left to right across the periodic table. However, what actually happens is that the atom gets smaller as you go left to right. The reason for this is you have more protons attracting more electrons that are in the same energy level. So if we go back to the Bohr kind of model here, the nucleus, first energy level, second energy level, third energy level. So let's say we're going across from sodium to argon in the third energy level. We would have 1 electron in sodium, 2, 3, all the way up to 8 electrons in this third energy level. Now we know the first 2 go into s orbitals, the rest go into p orbitals, so it doesn't look exactly like this. But you can get a general idea. The third energy level is further away from the nucleus. However, all of these electrons that are being added are going into the same energy level, so the same general distance from the nucleus. But now you have more negatives, and you're adding protons for every element, so more positives. So this outer energy level gets pulled more tightly into the nucleus. And that's why going left to right, we actually decrease in size. Doesn't seem to make a lot of sense, but it has to do with the fact that you're adding more electrons to the same energy level. You have more protons to attract those negatively charged electrons, and since they're going into the same energy level, they're the same general distance from the nucleus, so that increased attraction pulls everything in closer together. The trend as you go down the periodic table is that the atoms get larger. This, for the same type, we use that Bohr type model here. So if we go from the first energy level, fill it with its 2 electrons, the s orbital, the next electrons get added into the second energy level. So even though we have an extra proton in the nucleus, this electron is out further away from the nucleus than the 2 that were in the 1s, so the atom gets larger. And in some ways, we actually get a shielding effect. These lower energy electrons in the first energy level shield some of the positive charge from the electron further away. And we see this as we get higher and higher energy levels. So as we go down the periodic table, it increases in size. So if we look at a chart of this, you can see for a lot of the elements here, you see the atoms getting smaller as they travel to the right, and smaller as you go up. So up and to the right gets smaller, and the smallest element on the periodic table is here. The largest element will be down in the lower left-hand corner. This does not include the bottom row, so francium is actually our largest element. So it increases down and to the left, decreases up and to the right. Another trend that follows a pattern on the periodic table is ionization energy. Ionization energy is the energy needed to remove an electron from the neutral atom of a gas. Elements with low ionization energy are easy to remove an electron from, and therefore easily form cations. Elements with high ionization energies are very hard to remove an electron from, and therefore usually actually gain electrons or are not ionized at all. So the low ionization energy elements that easily remove an electron are things like the alkali metals, which have the lowest ionization energy. They have only 1 valence electron. It's very easy to remove that 1 electron from the outer shell of the atom. High ionization energy are those elements that have a lot of valence electrons. Most of that outer energy level is full. It's very difficult to remove an electron because the atom is either completely stable with a full outer energy level or very close to stable and would prefer actually to gain an electron rather than lose the electron. So our trend in ionization energy increases as we go up and to the right. So it's the opposite of atomic radius, and that actually makes a lot of sense. The further an electron is away from the nucleus, so if we have one atom with an electron way out here, and we have another atom with an electron right near the nucleus, it's going to be a lot easier to pull this electron off because it's a lot further away from the positive charge that's attracting it. Whereas this one, very close to the positive charge that's attracting it, will take a lot more energy to remove. And the more completely stable the atom is, moving to the right, the higher the ionization energy. Another trend is electron affinity. This is the attraction that atoms have for electrons. This increases left to right, decreases top to bottom. So this is the attraction that the individual atom has to pull its electrons towards the nucleus. So as its outer shell electrons. So as you move left to right, you're pulling in those electrons more tightly, all in the same energy level. Top to bottom, you're adding energy levels, so it's harder to attract those electrons. So these are a couple of properties that show periodic law, and we can see based on trends on the periodic table which one will be higher or lower based on their placement.